story that stands really at the crossroads of mathematics and politics. We don't often see that. We know that in the world of politics, there's often a lot of arguing. The lines between what some people think we should do and shouldn't do are often gray and hard to discern. And in mathematics, at least, we like to think that there are much cleaner lines, that 2 plus 2 is assuredly 4. And yet, in this narrative, in this story that I have for you today, we see that relationship between the mathematics and the politics. And the politics is interesting because the mathematics is messy. Or maybe the mathematics is interesting because of the natural messiness of politics. So the story has its preamble really in the Constitution itself. So Article 1, Section 2 of the Constitution is the section that talks about how the House of Representatives is supposed to receive a certain number to receive its population. And we all know the history of the Great Compromise that led to the adoption of the Senate, where every state gets an equal number of representatives, and to the House of Representatives, where that population, or the number that you send, is supposed to be based on how many people are living in your state, or the population. The interesting thing about this article is that other than stating that, it appears to be a little bit vague. The relevant language for us is the first sentence. Representatives and direct taxes shall be apportioned among several states, which may be included within this union according to their respective numbers. All of this is to say, based on the number in the state, we then determine proportionally the number of representatives that state sends to the House. Now, before we get too far ahead of ourselves, recall that this is important not just for representation in the House, but it also has great bearing on how presidents are elected. Because the number of delegates sent into the Electoral College is very much influenced by the number of representatives that state has in the House of Representatives. Now, I highlighted another line here. I just want to draw your attention to it because we're going to come back to it later. But there's this other slight qualifier here. It's the only part of it that actually addresses somehow the question of what numbers. And the Constitution says that the number of representatives shall not exceed 1 for every 30,000. So in other words, the Constitution is trying to ensure that we don't get a really big house where you have one representative representing a very small number of people. So it's trying to control for that a little bit. Now, I left out a lot of language here. So for those of you that teach the Constitution, you know there's some language missing. And it's important for us to note, at least right now, that some of the language in this article was amended by one of the amendments. Does anybody know which one? So it's between 13 and 15. 14th Amendment. Why would the 14th Amendment have some interest in this article of the Constitution?
They allowed African Americans to...
Yeah, because the language I left out starts to qualify that term numbers. Starts to describe effectively who counts in your state. In the original language, we know has some of this language about 3/5. And the 14th Amendment then repealed that provision and replaced it with another one. I'm less concerned about that controversy today, though the 14th Amendment is going to have a role to play as we trace the history of this particular problem. So before I set the stage, and really what I have to offer you today is about 60 to 70% history, and the rest of it is math. But they're very intertwined, and I hope that you see that as we go through the presentation. So what I have today is to start, just at the very beginning, it's the one task I'm going to ask you to do, is to just start thinking through why this might pose a problem. To start thinking through the mathematics, and to really actually just go back to put yourself in the shoes of the Founding Fathers. Maybe put yourselves in the shoes of those who are in the House, around 1790, who are on Washington's cabinet in 1790. And it comes time to apportion it. And to figure out how many representatives each state's going to send. How might you go about doing it? And I'm not going to have you fill this whole chart out, but I want you to take just about 30 seconds to think through this problem. And the first thing I want you to do is, with this little chart I've given you here, to start figuring out just a few things. Now, granted, I toyed around with the idea of actually giving you all the original states' populations, but this just takes a little bit long to set this up, and as we go through, it's going to very much help us to think in a very simplified form, so I don't have to start projecting upwards of a spreadsheet that has 50 rows in it for all the states. So I am concocting my own little nation here that just has 4 states and some pretty low population numbers. So what you need to know for this exercise is that each of these states has a population number, right? That doesn't change. But also, by statutes, our little House of Representatives is going to have 35 seats. You can't change that. That's written into statute. It's not the Constitution, but it is written into statute. So you're not allowed to mess with the number 35. So the question is, how do we go about determining, out of the 35 seats, how many should State A get? With 95 people living in State A. And I'm going to do this, there are numerous ways of thinking through this, right? One way is to say, okay, 95 is what percent of the population, let's apply that to the 35 seats, and that will get you the right answer. I want to think about this a little bit differently. What I'm very interested in is, how many people are there per delegate? What is the total number of people in our little country here? And with 35 delegates, how many people does each delegate represent? So can you take about 30 seconds, add up the population, and find me the people per delegate? That should be the same, by the way, for all 4 cells. I want people per delegate in the country. So a calculator might help, at least to go forward. Couple more seconds. Just want to get your wheels moving here. Okay, let's take a look at this together. Did you get 1,350 people in the country? Good. Okay, so we add those up. If you take 1,350 and you divide it by the 35 delegates, you should find out that one delegate represents 38.571 and some other decimals after that people. So every 38-ish people is represented by one delegate. Now the tricky thing in our calculations here is to make sure we don't round too early, particularly because we're going to do a couple of calculations. So we know that if you round an answer, and then use that rounded answer, and then round again, you can end up off by a good bit. So we want to try as best we can to keep numbers in memory here. So here's the question, right? If State A has 95 people, and every 38.571 people is supposed to get a delegate, I should be able to divide 95 by 38.571 and come up with the number of delegates. Okay? So I'm going to let you think through a little bit more of that later. This is not the only way to arrive at 2.463. There are at least 3 or 4 other ways I can think of that get us there. Right? The whole goal here is to try to think proportionally. The Constitution specifies that we're supposed to do this proportionally. There are 35 seats legislated by statute in my little fictitious country here. And I just want to figure out, based on basic percentages, proportions, or however you want to think about it, how many delegates each state should get. The actual calculation is something you can go home and do if you're interested. The much more important thing for me are the numbers that come out. Because right away we have a fundamental problem. And it was a problem that was always going to exist. It's not surprising. What is the problem with the number of delegates, or the number of, I'm going to interchange delegates and representatives, right? So the number of representatives and the number of delegates, what's the problem with it right now? what does that mean the numbers aren't even?
So for state A, you have 2.463. So is that, how do you proportion 2.5 delegates?
Okay, so the numbers are not whole numbers, right? The problem is we have fractional delegates. It makes great sense to me at being in state A that I should send 2 people. It also makes great sense that I should send 3 people. I have a little bit of trouble thinking about what it would mean to send 2.463 people. Particularly because I'm pretty sure there's some parts of the Constitution, at least, that says we should probably not start cutting people up into fractions and sending them to Congress. Yeah, so this is a real issue. Now, this is not an issue that was absent from the minds of the Founding Fathers when they're starting to write the Constitution. I don't have historical evidence of that, but there's no way that that could be. Anytime you're dealing with proportions and populations, you are almost always going to get fractional numbers out of this. Particularly when we're not even dealing with nice numbers like 95. We're dealing with population numbers that are 602,394. It's highly unlikely you're going to end up with a whole number anywhere, let alone across the board. The Founding Fathers had to have known about that. But they chose, and that's an interesting thing to think about, they chose not to address what to do with this in the Constitution. They left that to a later decision. And it's because of that decision, because of the messiness of the math, and because of that decision not to address it in the constitutional text itself, that we have such a fascinating history. So the question is, what do we do? The first obvious answer is, we just round, right? This makes great sense. So I'm going to go ahead and round them. I'm going to take 2.4 and take it down to 2. 7.9 makes great sense. That's really close to 8. 11 is closer to 11. 13 is closer to 13. This makes pretty good common sense to most people. What's the problem from a legislative point of view with doing this? I don't get 35 representatives. Now remember, that's part of the statute. Congress has to pass the number of people in the House. And I don't get that legislated amount. I end up short. I don't always end up short. Sometimes it might work. Sometimes you end up high. It all depends on what those decimals are. So somebody usually says, well, why don't you just adjust it and say we're going to have 34 members? So again, that's statute. Now in theory, Congress could pass a new statute saying 34. Here's the problem. How did we arrive at 34? We used the number 35. So if you're going to say there's 34 representatives, you're going to have to go back and do another reapportionment. Because now you should have a certain fraction, not of 35, but of 34. And when you do that, you might compound the problem. In fact, it can be shown that in some examples, you just bounce back and forth between 34 and 35, 34 and 35. So it does no good, even from a legislative point of view, to say, let's just change the House size. We could do it, but it may not solve the math problem. So let me take you back. Because the year is 1791. And in 1791, President Washington was well aware of this issue. Congress was well aware of this issue. And they knew they needed to come up with a method for definitively deciding how many representatives each state is going to get. So Secretary of the Treasury, Alexander Hamilton, gets a hold of this, and he writes President Washington a letter. And he describes a method for dealing with this. And here's what Alexander Hamilton says. He says, look, I'm not going to mess with the conventional rounding, because that just gets us in trouble, and I'm not sure what to do from there. What we're going to do is just round everybody down, just across the board. I'm not going to deal with those decimals at first. I'm going to round everybody down, and I'm going to figure out how many seats I've just doled out. And then I'm going to figure out how short I am, and then I'm going to give those seats out one at a time to those people that are closest to being rounded up. So let me take a look at this example. You have the example in front of you. I think this is on the back. This is the last time I'll ask you to write. So let me take you through Alexander Hamilton's method. He says, look, go through the same thing. Abide by the Constitution by doing this proportionally. Fine, determine that State A gets 2.463 delegates. But just round down, call it 2. Chop off those decimals. State B, don't round it up. Round State B down as well. Round State C down, round State D down. When I do that, I get 33 delegates. Now just remind me, how many am I supposed to have? 35. So how short am I? 2. Can you just pencil in very quickly who gets the extra delegates and then fill in that chart? And I promise it's the last time I'll ask you to write. Who is the first person that is really, really close to rounding up? State what? State B. And I think that makes pretty good common sense to people. If you're going to round everyone down and someone's supposed to get an extra one, it should be B. I mean, they were really close to 8 to begin with. A few extra people in their states, and they would have had an 8 point something anyway. So we're going to give them a state. Who's the next one? A at 2.463. Right? So A and B get an extra delegate. That gives me my 35, and I'm good to go. Make sense? For those of you that looked at the original numbers and said something like, well, I think that we should look at those who seem to have gotten cheated by just a hair at the beginning and give them the extra delegates, you probably looked at something like State A and said, oh, they were almost 2.5. If they were 2.5, they would have gotten one and then give it to them. It can be shown that that way of thinking leads to the exact same results as Hamilton. Basically, both methods are looking at who was closest. Who was closest to going up? Now, the fascinating thing is most people, when they see Hamilton's method, they think, this is pretty fair. I mean, why would you ever want another method? And that's what we're going to find out. Thomas Jefferson, also a pretty important person at the time, also in Washington's cabinet, Secretary of the State. He also writes a letter to President Washington, and he argues in his letter to Washington against the use of his colleague's method. He argues against the, quote, difficult and inobvious doctrine of fractions. He claims that his colleague is just playing mathematical gymnastics, and moreover, he claims that fractions are utterly unprovided for in the Constitution. But the Constitution does not mention the word fractions, and so we should not deal with them. It might be the first originalist argument in history. So I don't know if you can call it that, because he was like the original, right? It's a textualist argument, right? He's looking at the text, and he's saying, look, we shouldn't even deal with the fractions. A colleague of his, Edmund Jennings Rudolph, also from Virginia, who was the Attorney General, was a little bit harsher in his language and called Hamilton's method, for the same reason, utterly repugnant to the spirit of the Constitution. The word fraction does not exist, and therefore we should not even use fractions. Now, wait a minute, so what do? I mean, you can't just chop off those decimals. You can't just lose the fractions. Then you don't abide by the statute. You don't have the right number of seats. So Thomas Jefferson proposes something pretty ingenious. He says, look, the important thing, the unrepugnant spirit of the Constitution, is proportion. We're supposed to do this proportionally. If the numbers don't work out, just adjust the thing you're dividing by, but adjust it for everybody. So that in the end, you're still using people's population numbers, and you're still using them in proportions, and you're not monkeying around with any kind of rounding one way or the other. So here's what Jefferson says. He says, look, we're going to still round down. I'm going to start off the same way as my colleague Hamilton. But rather than trying to give the remaining seats out one seat at a time, I'm just going to adjust that number of people per delegate, and I'm going to adjust it until it works out. So let's take a look at this. So with the very same numbers, Jefferson, with 35 legislative seats, still computes those very same people per delegate, and he still computes that quota, that amount that a state is literally entitled to, 2.463 seats. But upon realizing that that adds to 33, rather than just trying to give it out, he says, look, just change that number. change 38.571 to another number until it works out. If you're low, pick one that makes it higher. If you're high, pick one that makes it lower. Pick another number. You can get the same results, by the way, by just pretending you have a different population. Now, Jefferson thinks this is fair, but obviously he's making up numbers at this point, but I think it's a fair way of making up numbers, because you're going to adjust this and you're going to apply it to all the states. So you're going to adjust their proportions in kind of an equal way. Now, I'm not going to take you through the guess and check of trying to figure this out. It turns out that with a number that's low, you need to start picking higher divisors to get this to work out. And you can start by saying, let's pretend it was 38, and see if that gets it for you. And if it doesn't, go down to 37. If you go down to 36, maybe 36 overshoots it, and you've got to go back up. It takes a little bit longer to do it, but you can always get it done just by being patient enough and trying to zero in on that first number that changes it. Turns out 36.5 works for our little fictitious example. If I do this, I come up with different quotas, but everybody's quota changed. So I'm not just going to try to assign these things willy-nilly based on who has higher decimals. I'm just going to apply a different divisor to everybody. I'm going to still round down, and when you do this, you'll get your required 35 seats. Now, I will leave it as a homework assignment for you to convince yourselves that this can always work. Some people see this and say, what if you just keep picking numbers and it never works? Boy, it will. Because again, if you're too low, eventually you drop down to the point where the divisor is so high, you're getting lots of delegates. And at some point, if you're patient enough, you just drop it down one at a time, eventually you're going to get there. 36.5 is not the only number that works. If you use 36.3, that would have also worked. The point is just to find one that works. And when it works, you always get the same numbers. So the question is there a difference? I mean, if there's no difference, then why argue about the methods, right? Maybe they always lead to the same thing. Well, of course, what makes the politics interesting is that the mathematics leads to different House seats. And this is what we see with Hamilton and Jefferson. We see that State A lost the seats, and State D picked up one. Now, where's Jefferson from?
Virginia.
What do you know about Virginia?
Large state.
It's a large state. Now, I know this is just one example up here, but who came out ahead using Jefferson's method? The largest state. Right? In fact, when you run these methods on the original apportionment figures, the original census figures, this is exactly what happened. Virginia went from 21 seats to 22 in moving from Hamilton's method to Jefferson's method. And New Hampshire, a small state, went from 5 to 4. And in fact, this turns out almost always to be the case. It has been shown time and again that Jefferson's method typically favors large states. Whether they knew that at the time, boy, I'd like to think he did. Jefferson's method not only favors large states, but there's another interesting phenomenon that comes, right? So what I've put up here on this chart is the original population numbers, and I've put that original quota, that thing you have on your sheets, just using basic percentages, figuring out what percentage, how many seats a state's entitled to. And I want you to focus on our fictitious Virginia. I want you to look at State D, who originally had 33.962 in an original quota. I'm sorry. Let me back up. It doesn't work on the sheet I gave you. I had to concoct different numbers to get this to work, so don't look at your sheets. I have another setup here. And in this other setup, the original quota for State D is 33.962. Now, before you even look across the charts, what would any reasonable person say the only two options for State D should be? If they're entitled to 33.962 seats, what are the only reasonable options? 33 or 34, right? Using Jefferson's method, guess how many seats they get in this scenario? 35, which is baffling. It's not clear if Jefferson knew that his method favored large states to that extent. They actually can not only pick up one by ensuring that they're the one rounded up, they can pick up another one. And so Jefferson's method, at least mathematically, has a fundamental flaw. It violates something we call the quota rule. The quota rule says that the final apportioned number should be within 1 of your actual literal number. I can't give you 6.723 seats, but by goodness, we should give you at least 6 or 7, and it shouldn't be anything different. And Jefferson's method absolutely violates that quota rule. So it seems that it should be utterly disqualified. So let's back up to 1791. Hamilton, Secretary of the Treasury, sends Washington a letter, says, here's how I think this should be done. His arch rival, Thomas Jefferson, also in the cabinet, Secretary of State, writes another letter to Washington saying, this is just mathematical gymnastics. His colleague says it's repugnant to the spirit of the Constitution. And he says, here's how I think it should be done, President. Here's what happens. After much debate, Congress ends up approving a bill for a 120-member House. And they approve it using Hamilton's method. Jefferson loses. The bill goes up to President Washington, and President Washington vetoes it. Where's Washington from?
Virginia.
This is the first exercise of a presidential veto in American history. And it surrounds a mathematical controversy. Why does President Washington veto it? Well, we already said, because he's from Virginia. Yeah, but why does he say he vetoed it? In his letter to Congress, he cites 2 methods. One of them aligns with Jefferson's philosophy and says, look, you didn't apply the same divisor to everybody. If you back up from Hamilton's method and figure out what that divisor is, it's changed. And so you haven't really done this proportionally. But he gives another argument, which actually might have some teeth to it. It turns out that in Hamilton's method, with the original census numbers, there were 8 states for whom they had more than one representative for every 30,000. And Washington claims that's a violation of the article in the Constitution that deals with this. He makes a constitutional argument. Now, of course, his opponents would say, no. That article in the Constitution, when it says no more than one representative for every 30,000 people, they're talking about a national phenomenon. They're talking about your national population. It doesn't matter that it violates it for one particular state. Washington disagrees. Now, I know that's unusual because usually everyone's very clear on what the Constitution says. Washington vetoes the bill in the first exercise of the presidential veto in American history, passes it back down. The House passes a new bill, and they adopt Jefferson's method. Jefferson comes out the victor. But they do, however, adjust the number to 105 seats. And in doing so, as they adjust that number, they minimize the impact that it has in some of the larger states. So remember, Jefferson's method won't always violate the quota rule. It won't always give precedence to larger states, but it quite often does. Sometimes you can fix that by just changing the number of seats, and that's within Congress's power to do. So they tried to kill 2 birds with 1 stone. Fast forward to 1832. We have our second battle here. John Quincy Adams versus Daniel Webster. And after our very long sort of preamble, chapter 0, we finally come to chapter 1, where we have the introduction of our protagonist. And that's going to be hard to see until I get to the end. But I claim that our protagonist is Daniel Webster's method. I don't know if Daniel Webster's the protagonist, and he looks actually really grumpy to me. But his method is going to end up being at least the sort of the fallen hero of our story today. But they're in a battle. They're actually not entirely battling with each other. They're both from Massachusetts, in fact. They do have a tension between which one of their methods they think Congress should adopt, but really they're trying to battle Thomas Jefferson's method. John Quincy Adams comes in and he says, look, I like where Jefferson's going. We're not going to get back to Hamilton because there's at least been some constitutional argument that that's not right. But I think the way that Jefferson did this is not fair. So I'm going to do exactly what he says, but instead of rounding down, round up. Just round everyone up, and if you don't get the right number of seats, adjust the divisor. It's absolutely identical to Jefferson's method, but he says you round up. And you adjust the number of delegates until it works. What do you know about Massachusetts? Very small. John Quincy Adams' method favors small states almost to an equal degree as Jefferson's method favors large states. His colleague from Massachusetts saw through this a little bit and said, look, we're not going to get that through. I propose that we adopt a compromise. We, in fact, are going to do exactly what Jefferson said. I like this idea of adjusting the divisors. It seems to alleviate the concerns about the constitutional language. But instead of automatically rounding down, instead of automatically rounding up, we are going to conventionally round. Just that elementary school rounding. If you're 0.5 or higher, you go up. If you're lower than that, you go down. And if it doesn't work, adjust the divisor. Now that seems really fair. So John Quincy Adams proposes his method to Congress, and it fails to pass. Daniel Webster proposes his method, and it also fails to pass. And Congress, in 1832, passes a bill retaining Jefferson's method, but in fact changes the size of the House to 2/4. Jefferson's method continues to win the day. Now, before we go too much farther, you'll notice a lot of the years that we're putting up, right? 91, 32. What's significant about these years? Generally, they're close to what? It's not always an election, but they're shortly after
Census.
the decade. So they're shortly after the what?
Census.
The census. So this is the problem, right? Because Congress kept passing bills to apportion the House now, to assume a number of House seats now, to come up with a method of apportionment now, every 10 years they had to go back through this. So every 10 years there was an argument like this. So after the census numbers come in, they're given, I think, 3 years to work this out. And so you're going to see a lot of numbers like 32, right? 11, 23. Numbers that are shortly after the census takes place. So in this battle that John Quincy Adams and Daniel Webster proposed, they don't win, and Jefferson wins. But in 1842, following that census, Webster finally wins out. We are able to convince Congress that Webster's method is much more fair, and the House size is in fact reduced to 223. They thought that it was getting too big. Who's not won yet? Hamilton, right? In fact, one of the first people to propose a solution. So what happens in 1842 is that Hamilton finally gets a victory. But it's an unlikely source. So what we see here is Representative Samuel Linton, who proposes a method to Congress in 1852, adopting a different method that was, for a while, called the Vinton Method. The problem with the Vinton Method is it's a very thinly veiled version of Hamilton's method. It modifies the language a little bit and the steps taken, but in the end, it really is the same method. So most books now will not even refer to it as the Vinton Method. At best, you're going to get it called the Hamilton-Vinton Method. But it really is the same thing. So in 1852, with a House size of 234, they finally adopt Hamilton's method. But here's the kicker. It wasn't just an adoption of Hamilton's method. It was that particular House size of 234. 234 happened to be a size for which Webster's method and Hamilton's method gave the exact same apportionment for every state. And this is a theme that we'll see through congressional history. When they can't agree, just kind of keep the status quo or give in and change it, but adopt a House size for which the methods don't differ. That they're going to agree and everybody goes home happy. In 1872, we have a very, very unique year. Perhaps the most unique year, certainly in the history of the problem we're talking about. Maybe one of the more unique years in presidential election history. So what happens in 1872? So first of all, what do you know about the year 1872? This occurs very close to something else. The what?
Civil War.
Yeah. So actually, 1872 is the first time that apportionment was reconsidered following the 14th Amendment. And so what we know is sort of following the census of 1870, the population numbers changed quite a bit. With the 14th Amendment repealing that 3/5 compromise, we now have very different populations in the states. So this is already contentious, because we're already going to try to do apportionment of the House based on radically different population numbers. So the House, in a compromise, chooses a size of 238. And this is, again, a House size for which Websters and Hamilton's gives the same apportionment. Now, so far so good. That's pretty normal. Then something very unique happens. In a very bizarre move, a couple months later, Congress passes a Supplemental Act. And the Supplemental Act gives 9 additional representatives to various northern states. But it does so without any regard of population. We apportioned the House based on population and then gave out 9 seats. It's not like it adopted 9 seats and reapportioned the House, knowing that it would favor northern seats. No, it completely violates the Constitution by apportioning the House and then giving out 9 handouts. And the consequences are rather interesting. So Hamilton's Act wins out, sort of. Because in 1876, we have the election of the Ohio governor, Rutherford B. Hayes, as he becomes the President of the United States. Now, there is a lot of controversy surrounding the election of Hayes. First of all, as his opponent, Samuel Tilden from New York, received 184 electoral votes. It required 185 to win, but there were 20 contested electoral votes. Some of them from various states because of fraud on both parties. So the entire state was being contested. There was at least one case of one elector from one state where that particular vote was contested because of his eligibility. So this was already a contested election. Tilden's the Democrat, Rutherford B. Hayes is the Republican. We effectively have 20 delegates and their votes hanging in the balance. Here's the thing. Had the 9 seats not been given out, it's very easy to demonstrate that Samuel Tilden is elected president. So Rutherford B. Hayes ends up winning this election through a compromise, but through a compromise that resulted from a botched apportionment. An apportionment that should have never happened, because after the apportionment was decided, 9 extra seats were handed out. It was down to the wire, folks. In 1876, Inauguration Day was March 4th. A compromise was not reached until March 2nd. A committee was supposed to be appointed. A committee that was consisted of 5 House of Representatives, 5 senators, 5 Supreme Court justices. An odd number, perhaps. They made sure they had 7 Democrats and 7 Republicans, and they did their best to pick one Supreme Court justice who was very respected by both parties as being as neutral as possible. Unfortunately, the Democrats tried to buy out that Supreme Court justice by offering him a seat in the Senate, which I find really interesting. If I'm thinking of what position I would rather hold, I'm not sure it's a senator over a Supreme Court justice. Supreme Court justice ends up taking the deal, but removing himself from the committee, much to the dismay of his Democratic colleagues. They pick another justice who admittedly had some Republican leanings. Controversy erupts, outrage is present, the Democrats start filibustering the proposal coming back from the recommendation of this committee. The filibuster lasts quite a while. March 2nd approaches, there's still no candidates for the inauguration day of March 4th. Representatives of both sides finally meet at Wormley's Hotel in Washington, D.C., and they work out a compromise, by which, interestingly enough, they concede the presidency to the Republican, who was behind, minus the contested votes, giving him the 20 votes, giving him a 1 electoral victory over his Democratic colleague. But the compromise is that upon taking office, Rutherford B. Hayes was to remove all troops from the southern states, all federal troops. And in fact, that the federal government was now to recognize the elected Democratic governments of these southern states that until then were, quote, unredeemed southern states. And effectively, because of a botched apportionment, because of a tense election already, we have the end of Reconstruction in American history. So here's the problem. Things get worse for Mr. Hamilton, or rather for his method. Because after this, people start paying a lot more attention to the methods of apportionment and the problems that might come up from it. In 1880, the chief clerk of the census office, C.W. Seton, computes the apportionment method of Hamilton for all house sizes between 275 and 350. And remember, up until this point, we basically had the House solving this controversy, coming up with a compromise, not based on the method, but by picking a house size. And being a mathematician from the census office, C.W. Seton says, I'd like to find out what happens with these new census numbers for all house sizes between 275 and 350. And something very interesting happens. If 299 is the magic number, Alabama was to receive 8. If 300 is the magical number, using Hamilton's method, Alabama gets 7. Now that may not seem like a big deal to you. So what? State loses a representative. We've seen this through all the methods. But I want you to process the reality of that for a minute, right? The population numbers don't change. He's working with the same population numbers. He's just changing the house size. So suppose I tell you that by statute, by population and whatnot, you're entitled to 20% of the dollar bills that are in my pocket. We're not splitting dollars. I literally have a bunch of $1 bills. And you're entitled to 20% of those, right? And let's suppose that because of that, you're entitled to $14. If I take the number of bills in my pocket and I add more to them, what should happen to the amount that you get if you're still entitled to that same 20%? It should be more, or at least the same, right? It might be the same. I mean, the rounding and all of this might work out so that you don't make it up, right? But if you're entitled to 20%, I mean, 20% of a greater number should be greater. So if it's greater, you should at least stay the same, and potentially you should go up. What I'm telling you happened with Alabama is the opposite. Using Hamilton's method, when they were supposed to get a certain percentage of 299 seats, that answer was 8. Given that same percentage in 300 seats, their number is now 7. You raise the number of seats, you keep the same percentages, and my count goes down? That just seems very, very counterintuitive. It's curious how it happens, but it seems very unfair. I mean, obviously if we change populations, if we change the number of seats down, I understand we might lose seats, but you raise the number of seats and I lose one? I want to take a look at this in our fictitious example. I'm going to return to our original 1350. So, if you remember, these are the original numbers that came out of our little experiment here. With choice A getting 3 delegates, and choice B getting 8, those were the 2 that were rounded up. And this is with 35 seats. I want you to focus on choice A. Okay? Choice A is entitled to a certain percentage of the 35 seats, and that comes out to be 3. Let's suppose we change the statute, and we say, look, there's now 36 seats. Look, A is sitting there thinking, okay, maybe I'll get that extra seat, maybe I won't. I understand I might not. In fact, there are others that might bump up. I've already been bumped up in my rounding. Probably not going to get that seat. But when we recompute it, what happens to choice A? It actually goes down. And you can imagine being from state A sitting here thinking, wait a minute. Like you're just increasing increase the number of representatives and I just lost a seat? That just doesn't seem right. And people agreed. And that was a problem. So in 1901, something similar happens. So by the way, Alabama didn't lose a seat. Remember, this is just based on the computations of seat. So it discloses that there's a problem. This is now known as the Alabama paradox. In 1901, people are getting more concerned about this. And they discover some similar problems here. The Census Bureau produces for Congress tables showing the apportionments based on Hamilton's method for all house sizes between 350 and 400. For every number between 350 and 400, Colorado gets 3 seats. For the number 357, they get 2. It's the one number. If that's the house size, they lose a seat. For every other number, they get 3. So Representative Albert J. Hopkins from Illinois, chairman of the House Committee on Apportionment, what does he do? He submits a bill to Congress adopting a size of 357. Colorado is ticked off. The bill fails. Webster's Method is adopted with a house size of 386. Hamilton's method is deemed quite unfair and unfit. We see it happen again, potentially again, as the Alabama paradox hits Maine. So if you recall, 386 was the house size that was chosen. Now it was chosen using Webster's method. So again, this is just a potential problem I'm picking out here. It went through with Webster's method, not Hamilton's. But using Hamilton's method, Maine is rather interesting because for numbers 383 through 385, it gets 4 seats. For 387 through 388, it gets 4 seats. But for that number 386 in between, it gets 3. And Representative Charles Littlefield from Maine writes a letter to the chairman of the Select Committee of the Census in which he says, "In Maine comes and out Maine goes. God help the state of Maine when mathematics reach for her and undertake to strike her down." The chairman responds, "Well, if Dame Rumor is to be credited, it is the seat of Littlefield that is the one in danger. And if the gentleman's statement be true that Maine is to be crippled by this loss, then I can see much force in the prayer he uttered here when he said, 'God help the state of Maine.'" Oh, the problems for Hamilton just continue. Webster's method continues to be used. But in 1907, Maine at least avenges its, quote, lost seat. Didn't really lose it, remember, because Webster's method ends up being adopted. But Maine gets its at least theoretical revenge. Because in 1907, Oklahoma becomes a state. Now, a reapportionment using Hamilton's method showed that the number of seats due to other states would be affected. Now, I need to explain this just a little bit, right? So it had typically been the practice throughout American history that when a new state is added, you adjust, at least temporarily, the number of seats in the House by a proportional number. Because the idea is that just by adding a state, your state representative shouldn't go down. Usually what happens is, if that number's not changed, they remove it for the next census. We actually saw this with the introduction of Alaska and Hawaii, that it was temporarily bumped up, and then during the next census it went back down to that 435 that we know. So in adding a new seat, obviously we just add a new state. If we just add a new state, clearly people's seats are going to go down. Oklahoma's going to get some seats. They got to take them from somewhere. To try to address that problem, Congress adds a proportional number of seats, right? So let's say that in our fictitious examples that every representative represents 50 people. If the state of Oklahoma has 100 people, we're going to add 2 seats to the House so that no one else is affected. The problem is it didn't work. Even in adding Oklahoma with the proportional number of seats, where it shouldn't have changed things, using Hamilton's method, when the House increased from 386 to 391 members, it made New York lose a seat, and Maine gained one. So again, it's a theoretical, but Maine at least is a theoretical victory. under the same method of Hamilton as it potentially could have gained a state. So it's a little bit like the Alabama paradox, where the house size increases. But in this case, we have a little bit different scenario because the house size is increasing by a proportional number to the population increase. So we'll demonstrate this. This turns out a little bit harder to concoct with smaller states, so I simplified the situation quite a bit. And I went with just a two-state union. A two-state union that has roughly 9,000 people in it. Right? So with 13 legislative seats, my apportionment is 2 and 11. So keeping that 2 and 11, let's say that state C joins the union. Now, if the people per delegate stays the same, if we're supposed to have the same number of delegates, so one delegate for roughly 700 people, C is going to be entitled to 4.28 delegates, which means we really should add 4 representatives to the House of Representatives. That's how much we decide to add. Now, for those of you that thought, wait a minute, that could have been 5, you get the same problems. So I'm going to stick with 4 because it's closer. Whether you round it up or round it down, the idea is to give C some delegates to make up for the fact that there's an increase in population because we don't want A or B to go down. So we're going to add 4 delegates, giving a total. So moving from 13 to 17 seats, right? And when we do that, we see some interesting things happen. We see that A, that had 2 delegates, goes up to 3. And B, that had 11 delegates, goes down to 10. So the introduction of a new state causes a change in the apportionment. Hamilton's method is just not doing well. And the problems for Hamilton continue. This is probably the most egregious one. So we have the Alabama paradox, where if you increase the number of seats without changing the population, it seems like your seats shouldn't go down, but they do, essentially. We have the new states paradox, where you enter a new state in the union, you give them the number of delegates and increase that number to the House so that it doesn't change the population of everyone else, and yet it does. But this one is funny. And the Providence of Maine. I was really hoping, particularly since it's a small state phenomenon, that it wasn't Maine, it was going to be Rhode Island, because that was going to be funny. So the Providence of Maine. There it goes. The Providence of Maine continues, and Jefferson rolls over in his grave. Because what happens is, between the census of 1990 and 1910, now again, these are theoretical problems, right? Because we're not adopting Hamilton's method. But mathematicians and congressmen and the Census Bureau are becoming very interested in this. So between the census of 1900 and 1910, compared with Maine, Virginia has more people in 1900. Virginia has more people in 1910. Virginia increases by more people from 1900 than 1910. And even by percentage, Virginia increases by more people compared to Maine. In every possible way that you can think, Virginia gets not just bigger, but bigger by a faster rate. In every way you can think to measure it. Now, what do you think theoretically would have happened under Hamilton's method? Virginia loses a seat. In fact, it lost a seat to Maine. This was later illustrated much more egregiously in the 1960s in a different situation. During this time, in a transition in looking at population numbers, North Dakota was the only state in the Union losing population. And yet, if we had used Hamilton's method, North Dakota would have gained a seat. Whereas others that were gaining in population would lose a seat to make up for it. I mean, this is completely against any common sense of how apportionment should work. Right? I lose people and I gain a seat. And this was pretty much the nail in the coffin for Mr. Hamilton's method. We're going to see this. This actually turned out to be the hardest one. I'm not going to lie to you. I actually started questioning this paradox. I started trying to get this to work out. And then I went back to the original numbers to verify that the mathematicians were right. And I was so frustrated, I was almost ready just to put up a spreadsheet of 40-some states up there. This was really hard to get to work out. And I think the answer somehow is that with a small number of states, you don't have enough numbers to play with. This took me upwards of hours, but it was a lot of fun. I won't go through all the details, but what we're looking here is a fictitious example of 24 seats in a population of 12,200 And I just want you to focus on states B and C. Using Hamilton's method, which is relatively straightforward. Again, folks, I want you to process for a minute when you first heard at the beginning of this talk, Hamilton's method. You think, actually, that's pretty common sense, right? Round everyone down, figure out how many seats there are to give out, and start giving them out to whoever's closest, right? It's the same mentality that those of you who said, wait, so just conventionally round, and if you need to give an extra state, give it to that 0.45 somebody because they're close to a 0.5. It's total common sense, and yet it leads to these bizarre paradoxes. So focus a little bit on states B and C. In B and C, we have 4 delegates and 9 delegates. So I'm going to change my population. Now on this slide, I'm going to repeat the old population and the new population. So I didn't display all the calculations, but some of it's pretty obvious, right? What happened to state B? It went up, right? What happened to state C? It also went up. But let's focus on C. In the old population, let's say 1960. In the 1960 population, who was bigger, C or B? C, right? 4,300 to 2,250. In the new population, who's bigger? So C starts bigger, C ends bigger. I'll let you do the subtraction, but C went, well, C is easy. How many people did C go up by? 88. Can you do B? Very easy too. So C starts higher, C ends higher, C increases by more people, and actually C, therefore, increases by a higher percentage of people, and yet look what happens to the delegates. We go from 4.9 to 5.8. You can check these numbers later. B actually gained a seat at the expense of C. It's completely counterintuitive, and we would say really radically unfair. This started getting people thinking. In 1911, Joseph Hill, chief statistician for the Census Bureau, writes a letter to the chairman of the House Committee on the Census, and he describes an entirely new approach to apportionment. And it was pretty good. It was pretty creative. He had a few problems and kinks that needed to be worked out, and I'm not going to go into his method. I'll focus on what happened with the fixes. Right? So he's got a pretty good method here. And what does the House do? Well, it just keeps adopting Webster's Method with a House size of 433. Now, there was a provision in 1911 that it started with 433, and then one representative was going to be given out to each of Arizona and New Mexico when they joined. And so here's the first time that we see the modern number of 435. Okay? And that's going to be with us for a while. The difficulties with Hill's method ended up being resolved by a Harvard University mathematician named Edward Huntington. So Huntington christens this technique as the method of equal proportions. And interestingly enough, of course, views the method as his own invention. It is not entirely true. And history agrees, because we now refer to this as the Huntington-Hill method. He certainly should be given credit for resolving the problems in Hill's method, but he certainly didn't invent it. He took the method and fixed it. And then Huntington became very impassioned by this, in a way that only a mathematician can be impassioned by mathematics. He devotes 20 years to tirelessly promoting this, both in congressional testimonies, in scientific journals, almost to the point where it's like, dude, you just keep resuscitating the same article. I'm not sure this is new research. He's really big on his own method. In 1920s, we had a problem. After the 1920 census, no new apportionment was done in Congress, because Congress, surprisingly, just simply couldn't agree. The only thing they could agree to was to appoint a committee of mathematicians to study the situation and to make a recommendations. And universally, the Huntington-Hill method gets a mathematical endorsement. So let's take a look at it. Okay, folks, it's a little bit more complicated, but I want you to categorize it under the same category as we've seen with Jefferson, Adams, and Webster. It's still a divisor method. It still says, hey, come up with some initial thing, and then if it doesn't work, adjust that divisor. And it's the very same divisor that's going to be adjusted. Jefferson says the initial thing is just to round everyone down, and if it doesn't work, fix the divisor. Adams says, no, that favors large states, and that's bad. You should round up, because that's neutral, and then it favors small states. Webster says, let's compromise on this, just do conventional rounding. But all three of them do some form of rounding, and then they adjust the divisor when it doesn't work out. The difference with Huntington Hill is that ingeniously, and actually the genius of Huntington was actually that he took a complicated method of Hill and not only fixed it, but also simplified it. He said, actually, it's not that complicated. It really is equivalent to this much simpler thing. The only complicated part is how do you come up with that initial thing? If you're not going to round down, you're not going to round up, you're not going to conventionally round down. Well, actually, he says there is something of a conventional rounding here. This is the one little deep part mathematically. We all know about the average. But average is actually an ambiguous term in mathematics. Like when we use the word mean, statisticians want to qualify that. You all are familiar with something called the arithmetic mean. What is the average between 10 and 20? It's 15. Now it's called an arithmetic mean because it has to do with addition. It has to do with 15 being in the middle, but being in the middle when you think of addition. That if you take 10 and you add 5, you get 15. And if you add that same 5 again, you get 20. So it's 5 away, but by away, I mean by addition. There's another mean in statistics called the geometric mean.
14.3.
The geometric mean has the same sense of being in the middle, but it has to do with multiplication. So the middle of 2 and 8 in terms of multiplication is actually 4. Because how do you get from 2 to 4 with multiplication? You multiply by 2. How do you get from 4 to 8? You multiply by 2. So it's odd for us to think about because we're not trained in that. We usually think of mean being that addition balance point. This is a multiplication balance point. Fascinatingly enough, statisticians have known for a while that the geometric mean is often more useful in describing statistics than the arithmetic mean. And the geometric mean, I'm not going to go into it, it has something to do with this square root. You multiply numbers together, and then you take the square root. Okay? That's about as deep as I'm going to go. But what Huntington Hill says is, look, take the values, take your quotas, right? I'm going to round them down like Jefferson, and then you're going to compute this geometric mean between the number and one more than a number. So if Jefferson has 2.469, you round down to 2, you're going to compute the geometric mean of 2 and 3. You're going to multiply 2 and 3 together and take the square root. If the original quota is less, round it down. If it's greater, round it up. Okay. All of that said, some complicated method, if it doesn't work, adjust the divisor. So in a very real way, it's a lot like Jefferson, Adams, and Webster. Right? But it seems to really alleviate this sort of small state, big state bias that exists. Right? So it falls squarely into that same category. So he's gaining some ground. In 1929, the Speaker of the House once again recommended that the National Academy of Sciences make an objective study of this problem. So remember, Congress has asked for a recommendation from a committee of mathematicians. The Speaker of the House asked for a second recommendation from the National Academy of Science. And universally, both committees say the most fair way of doing this, right, unapologetically, universally, is the Huntington Hill method. So Congress adopts Websters Method again. With a house size of 435. Again. So we see Webster's method just being continually promoted to the expense of this other method. Okay. Let's go to 1941. It's the last chapter in our story. In 1941, the president is Franklin D. Roosevelt. Franklin D. Roosevelt signs into law, finally, a bill that passes that follows the Huntington Hill method and fixes it at 435 seats. Now, it's important to realize a few things about this. Why is this the last chapter? Because actually, Roosevelt's bill that he signed into law not only does that, but it does something else. It says, look, unless you want to revisit this through legislation, the number is going to be 435. And the method is going to be the Huntington Hill method. You don't have to revisit this as Congress in 10 years if you don't want to. And they always have the prerogative of repealing it and passing new legislation. But prior to 1941, that provision was never written into the law, probably because they had such a hard time getting people to agree with it. So when the compromises were made, it was like, okay, well, we're just going to agree for the next 10 years. Like, we're more than happy to put that controversy off for another 10 years. Just wait till you see what happens in the 2000s with the national debt ceiling. We keep putting that off, too. So that's important to note, and that's why today we still have 435 seats. That's the good thing that this bill accomplished. Congress can choose to override it, to repeal it and pass new legislation if they want, but if they don't, de facto, this happens. Census numbers come out, the allotment, the apportionment is computed automatically, and that's communicated through other statutes to the states, and everybody's reapportioned. But that's not what makes it interesting. So there are two reasons in 1941 why Franklin Roosevelt was able, or got this through Congress and signed it. One of them is mathematical. They had yet another committee of mathematicians who were universally endorsing the Huntington-Hill method. So the experts in the field were unapologetically saying this is the right method. But something else happened. Webster's method, which is the current one on the books, and Huntington-Hill method differed by exactly 1 seat in the states of Arkansas and Michigan. Arkansas would pick up a seat, and Michigan would lose a seat. Why is this important? Because Arkansas was solidly Democratic, and Michigan was mostly Republican. What's Roosevelt? The Democrat. So the method that got through gave an extra seat to Arkansas. Now this is really interesting for me, because this is a decision that was made upon party lines. And there's evidence of this, because every Democrat in the House voted for the Huntington-Hill method, and every Republican in the House voted for Webster's method. Now that might strike you as kind of interesting, but here's where it gets really interesting. There are 6 Democrats in Michigan that voted in favor of the Huntington-Hill method. Michigan loses a seat under this method because it's solidly Republican. The Democrats in Congress had party loyalty trumping state loyalty. And I think that says something about where the country is compared to where it was with the Founding Fathers. I mean, maybe it means there's more party alignment back then within the state. I don't know. But I think it's interesting that the controversy in the early days of the country had everything to do with whether you were a big state or a small state, and it had everything to do with whether your state was going to lose or gain representatives. In Maine comes and out Maine goes. God help the state of Maine when mathematics plagues it. Right? By the time we get to 1941, the Democratic representatives in Michigan are happy to have Michigan lose a seat because they knew it would be a Republican seat. And I think that's just so interesting. It tells you how the country has changed since then. Before I wrap up, there are a couple methods that have been introduced throughout history. One of them comes from a congressman from South Carolina named William Lowndes, who was there from 1782 through 1822. He proposed a method that was similar to the Hamilton method. It never took root. It was a little bit more complicated. What Lowndes tried to do was to say that 0.8 that follows your decimal, your whole number, is not the same for everybody. A 4.8 is different than an 8.8. So he takes the 0.8 and he divides by the whole number. It really gives priority to small states in a real way. So he's got a little bit more complicated way. It never took root. At the time, though, in 1791, there was a mathematician from Dartmouth named James Dean who weighed in on this and also sent a letter to Washington and to Congress. Interestingly enough, his was a little bit like Lowndes, but it used something called the harmonic mean, which is another measure of statistics. I was really good and really diligent about finding pictures of the people that I'm talking about. Because I think that's one of the values of a PowerPoint. This is one picture I simply could not find. So I did the absolute best that I could. Forgive me. I have both a mathematical climax for you and a political climax The mathematical climax doesn't come until 1980. In 1980, a pair of mathematicians named Peyton Young and Mike Belinsky proved a rather interesting theorem that's of course now known as the Belinsky-Young theorem. And here's what they said. Any apportionment method that follows the quota rule. Remember the quota rule? If you're entitled to 7.3 seats, you should either get 7 or 8, but it shouldn't be something different. Jefferson's Method suffered from the quota rule. What I haven't told you is that so does Webster's. So did Adams. So does Huntington Hill. In fact, any divisor method has the potential of violating the quota rule. Some of them violate it more often than others. Well, the Belinsky-Young theorem is very interesting because it says, look, anything that follows the quota rule, so something like Hamilton's method, will in fact be subject to the three paradoxes. The Alabama paradox, the New State paradox, Oklahoma came in, and the population paradox. Those three really unfair things that seem very unfair about Hamilton's method, right? You can't hold both. They prove it's sometimes it's known as the Belinsky-Young impossibility. You can't do it. There is no perfectly fair method of apportionment. Now I want you to process that. It's not that we have not found one yet. That's the power of the Belinsky-Young theorem. They actually definitively prove that there isn't one there. That the minute you solve for the paradoxes, you have the potential of violating the quota rule. The minute you solve for the quota rule, you have the potential of having the three paradoxes. Now look, we know that the methods, they don't have the quota rule every time you apportion. They don't have the paradoxes every time you apportion. But there always, with certain numbers, will be those potentials. And so the big mathematical conclusion is that maybe the political controversy was right. There is no perfectly fair method. So you kind of have to pick one that you think either seems the most fair or satisfies you and your political needs, whether it's the state or the party. That's pretty impressive, actually. That's where mathematics gets very interesting. But there's another mathematical climax that really I would allow that to kind of be the political climax here. And that is, as mathematicians started really looking at this, and they started really developing ways of measuring the bias, they were able to do two things. First of all, the power of Huntington, what he did, he also definitively showed that all things being normal, with the divisor methods, there really are only 5. You can't, there's nothing else reasonable. Everything else is very, very far off. There really can only ever be 5. And all 5 of those showed up in the history we've been talking about. From Adams, Dean's, Huntington Hill's, Webster's, and Jefferson's. Now remember, Hamilton's was not a divisor method, it was very different. So Huntington proves that these are really the only 5. You can look and look and look, and under sort of normal circumstances, where you're not wanting things to be crazy far off, these are the only 5. But as mathematicians started trying to measure the bias, they confirmed what the Founding Fathers knew by instinct. They knew that Adams' method strongly favors small states, and that Jefferson's method strongly favors large states. But they started discovering that, in fact, Dean's method mildly favors small states. And Huntington Hills, as subtle as it sounds, Huntington Hills has a slight favor of small states in it. But when you look at Webster, which has something of an elegance to it, because it's simple, conventionally round, add the states, add the numbers where they seem, or adjust the divisor until it works. Seems to satisfy the Constitution's call for proportionality. Seems to be about as neutral as it can be. And yet that's not the method that we're using. There's more about Webster. Although it potentially violates the quota rule, it does so very, very rarely. And in fact, if you use Webster's method on the population of the United States, every year, based on population numbers, since it's existed, it will never have violated the quota rule. So you have a method that avoids all the paradoxes, almost never violates the quota rule, and has virtually no bias. That is as good as it gets. Because remember, the Belinsky-Young theorem says you can't have a method that doesn't have the paradoxes, never violates quota, and is unbiased. Webster almost gets it. And so I think I will let the mathematician Peyton Young have the final words. The principles that have been forged in the crucible of political debate are simple to state and appeal to our intuitions about fairness. First and foremost is even-handedness, or the lack of bias. All states, large or small, should get their fair share on average. Second, as the number of states goes up, or as the pie grows, no one's share should go down. Third, as populations change, a growing state should not give up states to a shrinking state. The implications are surprisingly strong. There is essentially one method, Webster's, that satisfies all of these three principles. It is commonly used in other representative democracies, where it goes by the name of St. Laug's method. In the United States, it was the law of the land in the 1840s, and again during the period from 1910 to 1940, when a combination of political interests and scientific confusion led to its abandonment. This ideal of one person, one vote, would be well served if Congress reinstated this simple and eminently sensible solution to the apportionment problem. And whether Young is right, I leave that up to you. I also leave it up to you to decide if Congress is simple and eminently sensible. You have, as Peter Kreeft says, you have suffered through the purgatory of listening to me ramble, and now comes the heaven of being able to ask some questions. So I am more than happy to field some questions that you have. Yes?
Did you have much difficulty finding a lot of information about this?
No. I had some difficulty corroborating some conflicting information. In fact, much to my dismay, the original textbook that I used when I first started this, after I started looking and researching the history and trying to find documents, I realized there were several mistakes in it, even in the dating of certain things and whose method was being used. Some of it seemed to oversimplify. I didn't realize there were some blips in the middle. Some of it just had some dates wrong. There are still one or two things in the presentation that I could go back and mention, but where the date, I'm pretty sure I have it right, but there are a couple, right, in today's day, the information age, oftentimes you have wrong information being corroborated, it's just being copied. The challenge was to corroborate it, to make sure as much as possible I have the correct dates and the correct information up there. Much of it was found by going after the actual legislation. And then, of course, you can get the dates, you can get the language that was passed, and that helped a great deal. That is the great blessing of the internet age, is that I can grab actual legislation from the United States government. Did I just say the U.S. government was trustable? Yes?
Did you ever look into during the shift in 1940 when Michigan, chose party over state loyalty? Did you ever look into what could have been the cause for that kind of shift? Did it have anything to do with the world wars that were going on, or was that not?
Oh, I'm sorry, the shift from state loyalty to party loyalty? I don't know that answer. But right, I think all of our experience and intuition suggests that this is true, right? I think that most people now intuitively identify with a party rather than with a state. I think if we sincerely examined our own biases, if we are strongly Republican and we found out that the state of Arizona, might lose a seat, but it was a Democratic seat, you might be like, okay. I don't know. I don't know that answer. I don't know if it has to do with mobility. It's a great question. What caused that shift in mentality? I would love to do some reading on that. I think if there's a book, you should tell me the book, and if there's not, I think that you should write it. But I think it is But I think it is a fascinating sort of thing about why that loyalty changed. Right?
Has anyone done any work speculating onto alternate American histories? Like, if this one would have been different, this way with this method, and the next one, the next one, the next one.
So I was with a group of teachers who asked something the same question. They said, they were referencing the original decision, because I didn't present the whole thing. I gave it to you at the beginning, and said, does anybody know the implications of Virginia gaining that vote? Gosh, again, I think that's a natural question that I would love to know more about, particularly when it comes down to sort of a single vote. The interesting thing about this history is it's often about one contested seat, right? I mean, the apportionment methods might have more than one seat changing hands, but it's never about a state gaining two. You know, it's always individual, about that tiny little quota that's there, right? And because it's only about one seat, it's usually a one-seat swing. Rarely do we see more than that. So it would be fascinating to go back through and look at, say, major pieces of legislation that passed in the wake of that and say, look, like, I mean, you have to make some assumptions. Like, you'd have to assume that people vote on certain lines, right? You vote on political, on their party lines, or maybe you vote on state lines. But that would be a great thing to know, you know, throughout history. We know at least one substantial implication of this is the election of Rupert v. Hayes. There surely have got to be some others when the Electoral College is that close. The House of Representatives is that close.
I know there's at least one story about the Hayes-Tilton elections, alternate district.
Yeah. Maybe one more?
How did the Webster method come to be called the same something method and used in other countries?
Yeah, I don't know the answer. It's done in another country. My presumption is that it was either discovered independently, which is likely. It's a simple enough method that it's highly unlikely that Webster would have been unique in thinking that. You know, again, I think once you kind of have an understanding of the divisor method, and you understand Jefferson, I mean, the ones that followed there are pretty natural next things. Like, what if you didn't round down? What if you rounded up? Well, that seems silly. What if you just conventionally round? So my guess is that it was discovered independently. That's not the only name it goes by. A lot of these methods exist in other countries for their apportionments of this, and then they go by a couple different names. And again, I don't think anybody would claim that Lowndes stole it. It's simple enough, it was likely independently discovered.
Thinking mathematically, I would think the one solution might be some kind of least squares minimization where the square of the differences is minimized.
Right. So this starts to get into some of the mathematics about how we measure bias. Right. How do you take those methods and then start to look at them and measure how biased they are? And some of that mathematics goes into showing that, hey, yeah, these are really the only 5 divisor methods. Everything else is just a variation on this in some way.
Well, why use a divisor method at all? Where you're changing the divisor. Why not compare the actual proportion to the theoretical proportion if you could have fractional delegates?
Sure.
And look at some kind of difference there.
Yeah, so I would have to think through the math, right? But I'm pretty sure if you just take the fractional seats and you start subtracting the other ones, I mean, you don't even need a least squares.
You could use absolute value.
Right? You could do that for individual values. I don't know this to be true, but my intuition says that it ends up being identical to something like Hamilton's method, where you end up giving seats. Because remember, with Hamilton's method, he says round down and dole out the seats. There's a very natural method. When I was talking with the group of teachers yesterday, there's a very natural method that says, well, just conventionally round, figure out how short you are, and give that out to the next one that's closest. My guess is, without going through the math, that it ends up being fairly equivalent or equivalent to something like that, and that it would end up being subject to these paradoxes, because it's not a divisor method. It's really the nature of the divisor method that makes you immune to the paradoxes, and then ironically you pick up the potential violation of the rule. Folks, you've been more than patient. I know it's been a long time. I know I talked a lot, which is rare for me, because I'm usually so quick and brief. I hope you have enjoyed my story, and I hope you have just a delightful weekend. Thank you so much.